from the world of the aerial to the world of the terrestrial. We go to Endeavor Aerospace and the Aura system. Presentation will be started by our assistant project manager, Gino.
Good morning, ladies and gentlemen. My name is Gino Farah. I'm assistant project manager for Team Visio, and today I will be going over the Rogue One mission. This will essentially be a recap of the beginning of the first presentation. Today, we will have two portions of the presentation, the Rogue One mission, and then we will take a deeper look into the Aura system. We will start with a mission summary, the concept of operations, the Rogue One system of systems validation, the Aura system validation, Aura systems validation, subsystems validation, and then conclusions and programmatics. Presenting with me today is Daniel Colantonia, who will end the presentation, and the rest of Endeavor Aerospace. I would also like to point out Manfred Hamburgo, our project manager, who will be assisting as the computer technician for this presentation. Here is the Visio design team layout consisting of two main teams, Invictus and Endeavor. They will both be responsible for creating separate systems for this project. There's also the integration and management team. Rogue One stands for the Reconnaissance Operation for Guided Unmanned Exploration 1, and its purpose is to obtain visual data of a remote area with unmanned vehicles. We have decided that the best way to achieve this goal is through three combined systems: the Vesta system, the Aura system, and a ground station system. The Vesta system, which will be made by Invictus, will be an autonomous hexacopter used to transport the Aura system to the location we wish to observe. The Aura system will be a manually operated rover that will explore the location we wish to observe. The ground station will consist of two computers and any components necessary to wirelessly communicate with the Aura and Vesta systems. I will now go over the concept of operations of the mission. We start with the combined Vesta and Aura systems at the Mos Eisley Spaceport, located here, with the ground station located on the third floor executive conference room of AC-1, the building we are currently inside of. We will then perform any pre-flight checks necessary before takeoff. Once we are ready for takeoff, we will start phase 2. Vesta and Aura will lift off and fly to the Yavin 4 ruins. Manfred, can you press the button? There we go. And then land. Once it has landed, Aura will deploy from the Vesta system. Aura will then begin its mission. And its mission will be to explore the Yavin 4 ruins while transmitting video data to the ground station. Once it has completed its mission, it will return and redock with the Vesta system and fly off. I would like to point out two servo motors that will be used to hold the Aura system in place during flight. Once it has taken off, it will fly back to the Mos Eisley Spaceport, land, and we will perform any post-flight checks, such as returning any systems to storage and cleaning up the mission area. Shown here is the Rogue One design structure tree. This shows all systems of systems, subsystems, and components. Each of these four partitions have their own objectives, constraints, and requirements that are necessary for mission success. The Rogue One system of systems has 8 primary objectives, these being that the Aura and Vesta system should be initiated at the center of the Mos Eisley Spaceport. The Vesta system should transport the Aura system to the Yavin 4 ruins. The Aura system should be deployed after the Vesta system has landed in an approved landing area within the Yavin 4 ruins. The Aura system should navigate the Yavin 4 ruins. It should generate detailed images of the Yavin 4 ruins. It should transmit visual data to the ground station. It should return to the Vesta system after the visual data has been transmitted to the ground station, and that the Vesta system should transport the Aura system to the Mos Eisley Spaceport after the Aura system has returned to the Vesta system. Additionally, we have 4 constraints, these being that the Rogue One system of systems will cost less than or equal to $3,800. The system of systems will have a mission duration of less than or equal to 60 minutes. The Vesta system will land in the grassy portion of the Yavin 4 ruins, and the Aura system will only navigate the grassy portions of the Yavin 4 ruins. I would now like to hand off the presentation to Barrick Smith, who will go over the Aura system.
Thank you, Gino. Before I begin, I'd like to introduce the presenter, my colleagues presenting with me today, Angela Prescott, Blake Maddox, Silas Grapp, Harold Ziegel, Nicholas Steiner, Michael Fusco, and Benjamin Barr. Let's jump into the system preliminary design. Shown here, once again, is our system of systems design structure tree. We are the ARA system. Right here. Zooming into our system design structure tree, we have the following subsystems and component level partitions. The ARA system is composed of the guidance, navigation and control, structure, locomotion, electronic power system, communications, and computation and data handling subsystems. We have the following objectives for the ARA system. These are the goals of the mission, and all of the primary objectives must be satisfied in order for us to achieve mission success. The ARA system should deploy from the VESA system in the Yavin 4 ruins, should be capable of navigating the Yavin 4 ruins, should generate detailed images of the Yavin 4 ruins, should broadcast the images to the ground station system, and should perform the mission in manual mode, meaning that there will be a human operator at the ground station controlling the vehicle in live time. Additionally, we have one secondary objective, which is expected to be satisfied. That is that the ARA system should dock with the VESA system once the detailed images have been broadcasted to the ground station. We also have a set of constraints on the design of our system. The ARA system will only navigate the grassy portions of the Yavin 4 ruins. Our total budget for the ARA system will be $720, and the total mission duration will be less than 60 minutes. We have a set of requirements. These are the design parameters that Endeavor Aerospace has determined must be met in order for the system to fulfill its system objectives. The ARA system shall have a total mass less than or equal to 3.5 kilograms, shall have a horizontal diagonal less than or equal to 50 centimeters, shall be able to climb a step height of 5 centimeters, and shall be stable when forward and sideways traversing a step of 5 centimeters. And it shall be able to drive up a ramp at an incline of 30 degrees. Jumping into our exterior design, we have 4 stepper motors that provide 4-wheel drive and differential steering to our 4 rubber-tired wheels. We have an IP video camera that can both record live video data and generate the detailed images at the ground station. This is an IP camera, which means it has its own IP address and will therefore be able to interface directly with our communication component instead of having to route through a microcontroller. We also have 4 ultrasonic sensors located at the corners of the vehicles in order to fill in the blind spots of the camera, and we have an antenna to broadcast the data. Opening up the hood, we have a primary microcontroller to handle all of our non-video sensor input and our communications, a modem which will interface for the communications, a magnetometer to determine our orientation states, a secondary microcontroller and motor driver boards to execute our movement commands and power the stepper motors, a power over Ethernet box to power our modem, and a network switch to allow both the IP camera and the primary microcontroller to interface with the modem simultaneously. We also have batteries to power our system, and a power distribution board to regulate the power that is supplied to each subsystem. At this point, I would like to pass it off to Angelo Crescendo to discuss numerical validation of the system requirements.
Thank you, Barrett. To start, we'll look at the mass requirement. Requirement 1.1 states that the ARA system shall have a total mass of less than or equal to 3.5 kilograms. As you can see at the bottom of the table, the current best estimate for our mass is right around 2.6 kilograms, thus validating requirement 1.1. Requirement 1.2 states that the ARA system's horizontal diagonal shall be less than or equal to 50 centimeters. From this top-down view of our CATIA model, and depicted by the orange line, you can see that the largest horizontal diagonal is 44.8 centimeters, thus validating this requirement. Requirement 1.3 states that the ARA system shall be able to climb a step greater than or equal to 5 centimeters. For this, we had to set up a situation with a wheel going over a vertical step height around point P. Point P is the point of contact between the wheel and the ground, We took the sum of torques around this point to calculate the required force needed to climb over this point. That required force is 7.6 newtons, although the drive motors only allow for 4.7 newtons of force. Although, so this does not numerically validate this requirement, although in the maneuvering area, there are no vertical step heights of this scale, so this is a situation that we will not encounter. Additionally, with the assistance of our Gnc components, we will be able to foresee and avoid any obstacles within the area. Requirement 1.4 states that the ORA system shall be stable when forward traversing a step of 5 centimeters. Stable is defined as the system passively not tipping over. As you can see from the diagram, the center of mass is well between the 2 points of contact while on a step height, thus fitting our definition of stability and validating this requirement. Likewise, the ORA system shall be stable when sideways traversing a step of 5 centimeters. Again, the center of mass being well between the 2 points of contact with the ground, validating this requirement. Finally, the ORA system shall be able to drive up a ramp at an incline of 30 degrees. This is for the situation when we're redocking with the VESTA system. From here, we use the following equation to calculate that required force to drive up this ramp to be 3.2 newtons. And again, the deliverable force from the drive motors is 4.7 newtons, thus validating the requirement 1.6. In summary, all of our requirements at the system level are numerically validated with the exception of requirement 1.3. At this point, I'd like to transition and start by defining risk. The risk is on 2 scales, probability and severity. Severity ranging from negligible, where system objectives are not affected, to catastrophic, where one or more primary objectives are completely prevented. At the system level, we have identified 7 major risks. Number 4 being the most notable, where we lose connection to the ground station system. Risks 1, 2, and 3, respectively, being we cannot deploy from the VESTA system, the VESTA system interferes with communications, or camera wires disconnect, or also note, as they are in column E, where they are catastrophic without mitigation. To mitigate these high-level risks, we will have to choose a robust docking actuator, use the VESTA system as a relay station, and tighten secure all wires before the mission operation. At this point, I would like to welcome up Blake Maddox to talk about the Guidance, Navigation, and Control Subsystem Preliminary Design.
Thank you, Angelo. I'm going to go over the Guidance, Navigation, and Control, otherwise known as the Gnc Subsystem. Currently, the Gnc Subsystem is located under the ORA system, and it consists of 3 components. The first component within the Gnc Subsystem is the state determination component, which will determine the orientation state of the ORA system during mission operation. The visual sensors component, which is the primary component that will relay visual data as well as take the detailed images required by the primary objectives, as well as the rangefinders component, which will assist the ORA operator in detecting obstacles that are outside the field of view of the range of the visual sensors. There are currently 2 subsystem objectives for the Gnc subsystem, as well as 2 critical component objectives. Critical components are components that have the most effect on accomplishing these subsystem objectives. The first subsystem objective for the Gnc is that it should allow the human operator to guide the ORA system through the Yavin 4 ruins in manual mode. The second objective is for the Gnc subsystem to generate detailed images of the Yavin 4 ruins. The first critical component objective is for the visual sensors component to relay visual data for the human operator of the ORA system to navigate through the ruins. The second critical component objective is that the visual sensors should generate the detailed images of the Yavin 4 ruins. Currently, there are no requirements for the Gnc subsystem level. However, there are 3 critical component level requirements that are essential to completing the objectives of the subsystem. The first critical component objective is the visual sensors component, which will that it shall provide the ORA system operator with a video resolution of quarter video graphic array, which is 320 by 240 pixels. The second requirement is that the visual sensors component shall provide a video frame rate of 15 frames greater than or equal to 15 frames per second. And the third requirement is that the visual sensors component shall generate images at a resolution of 720p, otherwise known as 1280 by 720 pixels. And for the numerical validation of the requirements stated before, we researched multiple components and have chosen a bullet IP camera as shown above. Please note that we will not use the component as bought. We will be taking apart the shell and using the internal components in order to fit it onto the ORA system. The current chosen specs within the bullet IP camera is that it can go as low as 240p and up to 1080p, which will meet the requirements, as well as it has 30 frames per second. And thus, as all requirements have been met, the numerical validation for each of the requirements has been satisfied. There are currently 6 risks that are identified with the Gnc subsystem. I would like to please note risk number 1 and risk number 4 as they are deemed catastrophic to mission success. The first risk is that each component is unable to interface properly with each other, thus creating problems during navigation. And risk number 4, which is failure to relay the visual data, which is essential for manual mode to be accepted. In order to mitigate the first risk is that we research each component thoroughly and ensure that each one can integrate properly before final component selection. The fourth risk can be mitigated by testing the integration and communication between the subsystem and system levels and to ensure that the data can be relayed. I would now like to hand it off to Silas Graff to talk about the structured subsystem preliminary design.
Thank you, Blake. Good morning. Today I'll be presenting the Structure Subsystem Preliminary Design. The Structure Subsystem has 3 components. These are the chassis component, which controls how the ORA system interfaces with the terrain while it is traversing through the Yavin ruins, the hardware bay component, which provides a mounting position for all the different subsystems of the ORA system, and the docking interface component, which works with the Vesta system to secure the ORA system while it is in flight to and from the Yavin ruins. The structure subsystem has 1 primary objective and 2 critical component objectives. These are that the structure subsystem should allow for maneuvering within the Yavin ruins, the chassis component should provide a rigid mounting position for the locomotion subsystem, and the hardware bay component should provide a rigid mounting position for the non-locomotion subsystems of the ORA system. The structure subsystem has 1 requirement and 2 critical component requirements. These are that the structure subsystem shall have a ground clearance of 5 centimeters or greater. The chassis component shall withstand a horizontal shear load less than or equal to 20 newtons applied at the mounting positions of the locomotion subsystem. The hardware bay component shall withstand a distributed load less than or equal to 120 newtons applied at the non-locomotion subsystem mounting positions in the negative z direction. Here, in order to meet these requirements, we have developed this preliminary design. It is composed primarily of 50-52 aluminum alloy sheet metal sections that have been brazed together. Here you can see some of the important features of this design, including the antenna ground plane, internal hardware bay struts, the removable hardware bay lid, as well as the motor mounting positions located there. In order to numerically validate the requirements of the structure subsystem, we measured the distance from the bottom of the hardware bay component to the point of contact between our wheel and the ground. In our CATIA model, we found this distance to be 6.5 centimeters. This numerically validates subsystem requirement 1.1. In order to numerically validate chassis component requirement 1.4, we created an ANSYS workbench model of the structure subsystem. We constrained one side of the vehicle at the mounting position for the motor components, and then applied a 20 Newton load at the mounting position for the motors on the other side of the vehicle. The maximum stress observed in this model did not exceed the ultimate strength of 50-52 aluminum. This numerically validates chassis component requirement 1.4. In order to numerically validate hardware bay component requirement 1.2, we created another ANSYS workbench model of our structure subsystem. We constrained the entire structure at all four motor mounting positions, and then applied the distributed 120 Newton load. The load was distributed across all of the mounting positions for the various Aura subsystems, and the load at each mounting position was proportional to the mass of each subsystem. The maximum stress observed in this model did not exceed the yield strength of 5052 aluminum. This numerically validates hardware bay component requirement 1.2. In summary, all structure subsystem requirements and critical component requirements have been successfully numerically validated. As you can see here, we have several risks identified for the structure subsystem, the most critical of which is the potential for our structure to become partially annealed during the brazing process. This would create what is called a heat-affected zone, and this could reduce the strength of our structure and potentially lead to premature structural failure. In order to mitigate this risk, we've reduced all stress concentrations near potential heat-affected zones, specifically near the brazing joints. We have also used finite element analysis to identify any regions of high stress that are near a brazing joint or other heat-affected zone. And we plan to conduct hardness tests at the structure in these locations once it has been fabricated in order to ensure that it has not been annealed past a critical point. Now I'd like to hand the presentation off to my colleague Harold Siegel to talk about our Locomotion Subsystem preliminary design.
Thank you, Silas. As you can see here on the design structure tree, locomotion is a subsystem of the Aura system and consists of two main components. The drive motors component, which will provide torque for the vehicle, and the wheels component, which will allow translation on the surface of the M4 roads. The locomotion subsystem has one primary objective, and that's that it should maneuver the Aura system in the M4 ruins, and one critical component objective in which the drive motors component should provide torque to the wheels component to maneuver the Aura system in the M4 roads. We have a pair of subsystem level requirements that state that the locomotion subsystem shall provide the Aura system with a speed greater than or equal to 0.05 meters per second, and a speed less than or equal to 1 meter per second. Additionally, we have a pair of critical component requirements that state that the drive motors component should provide a torque greater than or equal to 0.47 Newton meters and less than or equal to 1.32 Newton meters. Here we see the solution that the design team has developed to meet these objectives, constraints, and requirements. 4 stepper motors will be attached to 4 RC-style wheels. Because stepper motors are not typically used for this application, there will need to be an adapter fabricated by the design team to ensure that the two components are compatible. Here we see the component selection itself. 4 Adafruit PID 324 stepper motors will be purchased, 4 adapters will be fabricated here at the university by the team, and 4 RC style wheels will be purchased. To numerically validate subsystem requirement 1.1, the team found the maximum expected distance that needs to be traveled by the Aura system and divided that by the time spent in the mission environment collecting data and navigating. This was found to have a required speed of 0.05 meters per second to achieve this in the set amount of time, while our motors can deliver a top speed of 0.15 meters per second, numerically validating this requirement. To numerically validate the second subsystem level requirement, the team calculated the force that was necessary to overcome the force of friction, to scale the grade desired, and to accelerate to our maximum velocity in a desired amount of time. This was used to find the torque, and it was found that using an input of 1 meter per second for the velocity, that 95 Newton centimeters of torque would allow us to reach this. However, our chosen components will provide 80 Newton centimeters of torque, meaning that the speed should fall between the 0.05 meters per second and the 1 meter per second, numerically validating this requirement. To numerically validate the drive motors component requirement 1.1, we see the same procedure that we used on the previous slide, calculating the rolling resistance, grade resistance, and acceleration force to find the torque, this time using the minimum speed as the input. This requires a torque of 47 Newton centimeters to meet this speed, and our deliverable torque is 80 Newton centimeters, meaning that this requirement is also numerically validated. To numerically validate the second requirement for the component, The team found the maximum tractive torque, which is the torque that will cause the wheels to slip on the yabbing force surface, and that was found to be 132 Newton centimeters, while again, our motors will deliver 80 Newton centimeters, so we shouldn't see any slip on the surface, numerically validating this requirement. In summary, all 4 requirements just discussed have been numerically validated at this time. And now transition to risks. The team has identified a few key risks. I'll direct your attention to risks 1, 2, and 3 as they fall in the highest levels of severity, which could be a lack of torque provided by the wheel, or the motors, wheel slip on the surface, and adapter failure. To mitigate these risks, we'll have to do some rigorous testing of the motors. We'll do some terrain testing with the chosen wheels component, and to ensure that the adapter doesn't fail, we'll also do some rigorous testing and structural analysis. Now I'd like to welcome up Nicholas Steiner to discuss the EPS subsystem.
Thank you, Harold. Let's get right into it. So we have the EPS subsystem now, and it has 2 main components, the battery and the power distribution, or PD board. Our objectives are, at the subsystem level, that the electronic power subsystem should house the battery component as well as the power distribution board component. And the critical component objectives are that the battery component should store the electronic energy needed to power the Aura system for the mission duration. And the power distribution board should regulate the voltage output from the batteries to each of the components that requires electrical power. There are no requirements at the subsystem level, but at the component level, the battery component shall provide 40 watt-hours of electrical power to the Aura system, and the power distribution board shall provide 5 volts to the primary microcontroller, 5 volts to the switch, 12 volts to the drive motors, 12 volts to the visual sensors, and 24 volts to the power over Ethernet box. All of those numbers come from the spec sheets for all the different various components. Any more voltage than that, and we risk damaging those components. This is the wiring diagram for our subsystem here. So we have 2 11.1 volt, 4,500 milliamp hour batteries wired in series. That gives us a bus voltage of 22.2 volts and maintains our 4,500 milliamp hour rating there. The black dotted box shown all the way around these other 5 subcomponents is the power distribution board, and those 5 subcomponents are all DC-DC buck converters or voltage steppers. The blue ones are solder terminals in and out. The red one is a 5 volt USB output. Here is where the subsystem lies inside of the Aura system. It's important to note that the batteries are near the center. They carry a lot of the mass of the Aura subsystem, and we wanted to keep the center of mass near the geometric center of the Aura system. So this is how we've validated all of our requirements numerically. They all come from the spec sheet, and it's important to note that that right-hand column is the maximum power draw that we expect to see. It's the maximum amperage that each component can take in a sustainable way. Our max power draw is 36.9 watts. We expect to operate for roughly 1 hour, which gives us a total power of 36.9 watt hours. And our battery will provide 49.95 watt hours of electrical energy, thus validating that requirement. So in summary, we have numerically validated all of the component level requirements. And now we're going to talk a little bit more about risk. The main one to note here is risk number 5, and that is overdraw of the batteries could cause problems. Risks 1, 3, and 4 are also critical, and a lot of those have to do with the battery itself. So to mitigate these risks, we have identified these key things to do. As far as improper interfacing, it's not very likely to happen, but if it does happen, we're at a critical mission failure there. So we have to communicate with each other and make sure that we all have the same attachment methods for all of our components. We need to add heat sinks where necessary. We don't have any heat sink requirements as of yet because we don't really know until we have the components how much heat they're going to put out. Shock damage we're going to mitigate through either using ground straps while putting everything together. And power surge we have to mitigate through use of a constant current, constant voltage, or CCCV charging system that monitors cell voltages. That way we don't experience any overdraw of our batteries wired in series. And the main one down there, overdraw of the batteries, will be mitigated by increasing the power rating of the battery. The less power we take from the battery, the less likely it is that we're going to overdraw. Next, I would like to hand it off to Michael Fusco to talk about the communication subsystem.
Thank you, Nicholas. The communication subsystem is a subsystem of the ORA system and consists of 3 components. The modem component should modulate and demodulate digital signals for transmission and reception respectively. The antenna component should detect and produce radio signals, and the power over Ethernet box should power the modem component. First, the subsystem objectives. The communication subsystem should transmit visual and sensor data to the ground station system, either directly or relayed through the VESTA system. The communication subsystem should receive command data from the ground station system, either directly or relayed through the VESTA system. The constraints include that it will transmit and receive data on non-licensed frequencies. In this context, that means consumer frequencies. The communication subsystem will also connect to the wireless local area network created by the ground station communication subsystem. The subsystem requirements include that it shall transmit with a bit error rate greater than 0.01%, shall be capable of transmitting a data rate greater than or equal to 0.7 megabits per second, shall be capable of transmitting and receiving data over a line of sight distance greater than or equal to 215 meters, and shall be capable of transmitting data with an equivalent isotropically radiated power, or EIRP, greater than 27 decibel milliwatts, or dBm. Shown in this table are the current component selections to satisfy the communication subsystem requirements. The modem component has a transmission power of 28 dBm and a sensitivity of negative 83 dBm. The antenna has a gain of 4 dBi, and the power over Ethernet box is a passive injector and can supply up to 24 volts required by the modem. These components are shown with respect to the ORA system, with the addition of the switch component, which has not been reflected in the design structure tree yet, but will be in the future. The switch serves to connect the IP camera and the primary microcontroller to the modem simultaneously. Requirement 1.1 is validated by calculating a carrier to noise ratio, or CNR, greater than a required CNR to deliver network performance and signal quality. This CNR is calculated based on the modulation type, based on the channel data rate, the bandwidth, and the energy per bit to noise power ratio, which corresponds to the bit error rate. Given that the calculated CNR is 34.2 dB, which is greater than the required 12.9 dB, this requirement is numerically validated. Requirement 1.2 is validated by the fact that we can deliver network performance with our calculated CNR and has a channel data rate of 24 megabits per second. Requirement 1.3 is validated by the fact that the carrier power, C, in finding CNR uses the required line of sight distance of 215 meters. Requirement 1.4 is validated by calculating the carrier power from a signal sent by the ground station system, which should be greater than the sensitivity of the modem. The calculated carrier power is negative 51.7 dBm, which is greater than the required negative 83 dBm for modem sensitivity. Requirement 1.5 is numerically validated by looking at the components data sheets and finding EIRP, which you add the transmission power to the gain of the antenna. We found that we can give a EIRP of 32 dBm, which is greater than the required 27 dBm. In summary, all the requirements I've discussed are numerically validated. Shown here are the associated risks with the communication subsystem, including that we lose direct connection to the ground station system, the data rate is greater than the network bandwidth, and there's signal interference due to Wi-Fi crowding. Risk 1 is mitigated by the fact that we can use Vesta as a relay station. Risk 2 is addressed by the fact that we can use a different protocol, N-type, which provides up to 60 megabits per second channel data rate. And risk 3 is mitigated by the fact that with the modem selection, we can set different protocols and center frequencies to avoid transmitting on frequencies of equipment nearby. I would like to introduce Benjamin Barr to discuss the Computation and Data Handling Subsystem.
Thank you, Michael. Going right into it, the Computation and Data Handling Subsystem is under the ERAU system and contains 3 components. The first being the primary microcontroller component, which should process all of ERAU's sensor data. The secondary microcontroller component will process all of ERAU's command data, and the motor controller will relay the necessary power to the drive motor components of the Locomotion Subsystem. So the objective of this subsystem is that it should contain all the 3 components just discussed. Critical component constraint is that the primary microcontroller component will have an Ethernet port so that it can communicate with the ground station via the switch that Michael talked about. So a requirement of the motor controller component is that it shall relay less than or equal to 11 watts of power to the drive motor components of the Locomotion Subsystem. This is a table laid out of the selected components that satisfy the current requirements. So we have the Raspberry Pi 3 Model B Plus for the primary microcontroller, the Arduino Uno R3 for the secondary microcontroller, and the Adafruit Motor Shield version 2 for the motor controller itself. Then we laid out a block diagram showing the flow of logic into and out of the Computation and Data Handling Subsystem, denoted in green, from other components of other subsystems. Then we have a wiring diagram using a software called Fritzing that will show you the Arduino stack here. It has 2 motor shields stacked on top of it, so you cannot see the Arduino Uno underneath, but it is there. And then 4 drive motor components total connecting to the terminals of the motor shields. Then an I2C interface occurs between the Arduino Uno and the Raspberry Pi 3. And also using I2C, we have the the IMU of the Gnc subsystem, and then the 4 ultrasonic sensors of the Gnc subsystem connected to the Raspberry Pi. Not shown here is the connection to the motor shield separately to the jumper terminal that will relay power to the motor components. So for the motor controller component, requirement 1.2 numerical validation, we essentially looked at the chosen component's data sheet, finding the maximum operating voltage to be 13.5 volts and the maximum operating amperage to be 3 amps, and then calculating the maximum operating power using P equals VA to be 40.5 watts. This can be scaled down to satisfy the requirement of 11 watts, thus numerically validating the requirement. Then we laid out the risks for this subsystem. The most notable one is number 3, that could result in catastrophic failure for the ERA system. Number 3 is that electrostatic discharge or motor wire disconnects. And to mitigate this, we need to make sure we tightly fasten the motor wires to the connection terminals of the motor controller. So, make sure Endeavor Aerospace team members don't tamper with motor connections while the controller is active and powered, in order to prevent permanent damage to the motor controller's integrated circuits. Now I'd like to welcome up Daniel Colantonio to talk about the team's programmatics.
Thank you, Benjamin. So I'm going to be starting off with the System Assistant budget. We have a total of $3,800 to us, and of importance, we have allocated $220 to the ground station and $720 to the ERA system. From those $720, we have allocated the following amounts to the ERA subsystems: $75 to the Gnc, $71 to structures, $170 to communications, $125 to locomotion, $93 to EPS, and $134 to C&DH. We've left aside $52 also. For the ground station, we have allocated $90 to the modem, $40 to the patch antenna, and $50 to the router. Here is our current best estimate cost for all the components for the subsystems. This totals all to $657.60, which is well within our budget of $720. Here is management and integration labor hours, with most of our labor hours in engineering and administration. We have a total of 585 hours. This team was initiated on October 15th, halfway through the semester, which is why 585 is significantly lower than the total labor hours for Endeavor Aerospace's team of 2,106, with most of those going towards engineering too. We would like to acknowledge the following people, and with a huge shout out to Dr. Julio Benavides and Dr. Matthew Haslam. Without them, we would not be where we are today. We'd also like to thank the panel and the rest of the audience for joining us today. I'd now like to welcome up Endeavor Aerospace for questioning.
Thank you. Very good presentation, guys. Well done. First of all, just on your very last couple of slides, it's a comment I made to the last group, but not publicly. I made it to the afterwards. You've got what looks like a huge amount of administration in the program, and I don't think you mean that. I think it's technical. Well, it's technical administration. It's writing specs. It's doing the designs, that kind of stuff. Is that right?
That's correct, yes.
Okay. So I would show that. The administration sounds like, you're dealing with HR and you're dealing with all sorts of crappy stuff that we all have to do with the projects, but that's not the purpose there. But good program. One of the slides towards the end, you talk about ESD. And ESD is a problem. with programs like this? Do you ground yourselves when you're actually working hands-on with the electrical components?
Yes, that's the plan.
You'll have rails tracks.
Either do that or discharge directly before touching any components.
Okay. If it's really sensitive stuff, you really want to use wrist straps. If it's not so sensitive, then it doesn't matter quite so much. On the com stuff, you mentioned bit error rate several times, and it said that the system should transmit with a bit error rate of more than 0.01%. I think you mean it should be capable of, not that it will, because you want bit error rate of 0, you won't have that. But have I got that right? It's just going to be capable of doing that. It's not a design requirement.
That's right. And the requirement should really be less than.
Yeah. The requirement is less than, it's got to be capable of more than, but it's not a requirement for more than. Okay. I've got a whole ton of questions, but we'll run out of time. So let me just ask you another thing. You said early on you can't, I think, you can't do the step of 5 centimetres, is that right?
That's correct, yes.
Which you've got on the modeler there, you've got rams.
So that requirement of a 5 centimeter step is referring to a vertical step. And originally in our design process, when we went out to the Yavin 4 Ruins location, we were measuring what is the maximum height of any of the terrain out there, and we measured approximately 5 centimeters. So we assumed in our requirement a worst case scenario of a vertical step of 5 centimeters. Later on in the design process, we learned that that wasn't a good way to write a requirement, because even though that is the worst case scenario, hypothetically, that we could encounter, it's not very realistic of the needs of the mission. So if we wanted to increase our wheel size or increase our stepper motor output torque, we could meet that requirement as written. However, doing both of that would increase the mass of our system quite a bit, and since we need to be carried by the Vestas system, it's desirable for us to keep that low instead. So instead of meeting that requirement that's poorly worded as is, we're right now planning to, in the next phase, rewrite that requirement to be more indicative of the needs of the mission.
That's fine. I mean, modeling requirements is always a perfectly acceptable thing to do. And of course, much better to model the requirements than find you can't meet them and then have to model the design, because that's what it costs money. So that's a very good thing. You can always put bigger wheels on anyway, because you're a kilogram in the mass. So.
Yeah, that is correct.
Okay, well done, thanks.
Thank you.
Right, I'll echo again what he said. You're saying a good job. I forgot some questions that I meant to ask to the other team, so I will just bring them up to you guys. So, what were some of your guys', shall we say, less than shining moments, your lessons learned, both technical and as far as team dynamics? I don't know about you, but my team had a lot of interesting dynamics.
That's a great question. I think everybody on this team will probably give a slightly different answer. For myself, I would say that some of the biggest lessons learned are how the design process really flows from one phase to the next. And that also ties into the 5 centimeter vertical step. You know, at this point, once we're actually designing the system, we're figuring out things like, well, how much work really should go into writing those requirements so that they very accurately depict the needs of the mission, because we don't want to be required to add extra functionality that's not critical for mission success. And so that, to me, that would be the biggest thing from a technical perspective. From an interpersonal perspective, I think it would be nailing down communication, expectations for the other members of the team, making sure that everybody's on the same page about what's happening and what work should be done by each team member. Those are definitely very critical things for us to work out amongst ourselves.
I hope this doesn't disappoint you, but that doesn't change when you go into distribution. Okay, so we'll get to the high-level questions first, and then we'll go a little more detailed next. So first off, how do you use wheels?
So we did a detailed trade study on that early on in the semester. I'd like to defer that question to Harold.
We did consider a couple different designs, from as simple as basically a balloon on a string to a drone within a drone, because we love drones. But the wheel design seemed like you mentioned the lessons learned. And I guess one of the lessons learned was finding the design that meets the requirements, that requires, the smallest budget, the least amount of work, or the least amount of quality work, I should say. So we felt that the wheel design allowed us to easily traverse the mission environment without overcomplicating things, driving up our budget.
Okay, so I don't mean to pick on you for this answer, but were the metrics tied to that, or was it purely a choice made? Does that question make sense?
There was a decision matrix.
Okay.
So
Yes.
Okay, that's all I need to know. I'm gonna assume that you're gonna give me the same response for using step motors, right?
That's correct, yeah.
Okay, yeah, I was just curious why you chose step motors as well. It seemed interesting to me. Okay, let's go to slide 4, please. So, risk number 1, choose a robust docking actuator. What happens when it doesn't work even if it's more robust?
that's a great question. We don't have a mitigation for if the docking actuator fails at this time. We could potentially look into designing the docking actuators to such a tolerance that we deem that we can't really shake around or shake out of place while riding in the undercarriage, but we could still squeeze out of there even if they don't retract.
Okay, okay, that works. Yeah, the main reason I'm wondering is your system in particular seems like you may be subject to non-cooperative hardware, so I want to make sure that you guys have redundancy built in.
Yes.
In some places.
And those docking actuators are actually on the Vesta system.
Okay.
So they're the ones that are actually holding us into place.
Okay. Okay. All right. I guess this is more of a controls question. You guys are familiar with Martian rovers, right? Okay. Familiar with how most of them have 6 wheels, right?
Yes.
You guys know what kills most of them?
Wheel failure?
One wheel jams. What happens when one wheel jams?
On our system or on, so we don't have a mitigation for that, but we are expecting that in the duration that we're going to be operating in, that isn't going to be a significant probability.
So I'd actually disagree. I think you have mitigation. You have a motor on each end of the wheel. So that should help you a lot, and they're stepper motors. I only ask that though as for your control standpoint, if one of your wheels, one of your motors, something stops working in one of them, can you still move with only 3 cooperating? I'm not sure, since I haven't done that kind of thing, and I'm just curious if that can be done or if you can design it under redundancy. Because I can see that happening if you're in an environment that's hard to traverse.
Yes, we could hypothetically design the control law to be able to, during the mission, deactivate certain motors if need be. If one wheel becomes jammed, we can turn that one off and then only utilize the other ones. Like, let's say a corner wheel jams, we can deactivate this counterpart and then only use the front two to equalize that.
Okay. All right, I think one more, and we'll keep going from there. We'll do something a little more specific. Slide 60, please. Okay, so risk number 1, difficult to fabricate. Obtain experienced fabricator feedback on design. Has that been done yet?
I'd like to defer that question to Sales.
Yes, it has. I've talked to Mr. Jeff Hyatt, our experienced welding fabricator here on campus. He had lots of feedback about our design. He was the one who recommended the change from 60 to 61 aluminum that we had previously specified it for to something that's a little more easier to work with. He specified that we use 3003 aluminum alloy. I talked to him later, and I think we settled on 5052 aluminum as the better choice because it is a little more commercially available and has a little bit better brazing properties for our purposes.
Okay, good. Yeah, the way you had it worded up there had me worried that you hadn't done that yet. Just sitting here thinking this is a PDR that shouldn't be done.
Well, we left it as is because we were planning to continue to work with him to make sure our design is fabricatable.
Okay, all right. Maybe I was a little confused in what you're trying to communicate. Okay, and for risk number 3, why do a hardness test?
So I know it's a common procedure on aircraft. After you perform a weld, you do a hardness test at that location. When a substance is annealed, it will generally become softer and have a lower hardness than the initial hardness. So if we can measure a hardness of the original piece of stock material and compare that against the hardness test of the region that might have a heat affected zone, and if it's significantly softer, then we know it has been annealed. And most of the time, you should be also able to approximate the yield strength and ultimate tensile strength of the material based off the hardness.
Okay. I just asked that because I was talking to the other team about this as well. I was wondering what prevented you just from doing a simple stress test or a destructive test if you have time and budget. It was just curious to me that you chose hardness test out of it, but it would probably be least destructive and probably the least, I guess, intensive of the option. So fair enough. Overall, good job, you guys. Look forward to seeing it.
Thank you.
Yeah, again, great job. So I saw in your requirements that you always mention manual mode. Do you have like a tertiary requirement that you want to be able to perform this autonomously?
So we actually began with a tertiary objective to perform in autonomous mode. However, when we were in phase 2, we were doing more analysis on that, and we determined that inside of the time constraints of the project, that would be a lot more difficult to implement, especially because we're not a drone that has essentially a relatively unobstructed space to translate in. Since we have to move around, there's a lot of obstacles. The area inside of that black gate in the Yavin 4 ruins often has objects moving in and out because other on-campus clubs use that space for storage. So we don't even know where objects might be until the day of. And there aren't really a lot of clear visual callouts that we could use for autonomous navigation from a camera to be able to detect what's an object and what's the ground and whatnot. So that's why we ultimately determined that while we could do that in theory if we had enough time, for the time constraints we wouldn't have made.
Makes sense. So what is the purpose of your ultrasonic sensors then?
So the ultrasonic sensors essentially cover the blind spots of the camera. This camera has approximately a 90-degree field of view, so that does cover quite a bit of region in the front. However, when we are to turn or back up, and especially when we are trying to redock with the Visio system, these ultrasonic sensors give us a little bit wider field of view in the sides and especially in the back that we wouldn't be able to get from just a camera.
Cool. And I don't think I saw it in any of your guys' presentations, but who is responsible for the ground station?
The ground station is directly under management's authority, and also we have some team members from both teams that are working with them to make sure that our systems can interface correctly with the ground stations.
So I have one last question. On slide 70, you mentioned a coefficient of friction for, what is that for? How are you making sure that you can drive over all terrain?
I'll defer that question to Harold.
We used a coefficient of friction of grass and rubber between the two because that's the worst suspected terrain that we're going to encounter. We're not going to drive over much gravel or anything. We're only constrained to the grassy portions. So we assumed that grass would be the worst thing that we encountered, so we used that coefficient.
Cool. Good job, guys.